Hey guys, this is a video for MMAN2300 Assignment D. This is one of my favourite courses, so hopefully I'll get a few bonus marks for saying that. Alright, so today we'll be looking at chapters 5.6 to 5.7 in Mariam and Kraige, which is acceleration analysis of rigid bodies. This session will be broken down into three parts. The first part I'll introduce the basic concepts. The second part I will talk about rotation about a fixed axis as well as general plane motion. And the third part we'll go through an example together. So let's begin the first part. Motion can be considered as a combination of both translational and rotation about a point on the body. From our studies of kinematics, we know that the relative velocity equation is the velocity of B, point B here, is equal to the velocity of point B relative to A plus the velocity of A, where VB with respect to A is equal to omega times the length of AB. Similarly, our equation for relative acceleration is acceleration of B is equal to acceleration of A plus the acceleration of B relative to A. However, one thing does change here, and that's the acceleration of B with respect to A. This is broken down into a normal component and a tangential component as shown in the diagram here, where the tangential component is obviously tangential to the plane of motion, and the normal is perpendicular to the tangential. Consequently, we can see that the acceleration of A of B with respect to A is actually equal to omega squared times the length of AB, and that the tangential component is equal to the angular acceleration times the length of A, the length of the rod AB. That concludes section 1. So this section is going to be really quick. I just wanted to go through general plane motion and show that plane motion of a rigid body is just a combination of both translational and rotation. So even though we have a rigid body that's falling, we can separate it into two different components. One, it's moving in that direction in a translationally, and then two, it's rotating about a point. This is what led us to our general equation from the previous section, which is the acceleration of B is equal to the acceleration of B with respect to A plus acceleration of A. The breakdown is what you've seen before. This leads us on to rotation about a fixed axis, which is a special case which makes life a lot simpler. So as you can see from this rigid body here, it's rotating about point O in an anti-clockwise direction with angular velocity omega and angular acceleration alpha. AM is towards the center and AT is perpendicular to AM. So as we can see at point P, the acceleration of point P is equal to the acceleration of point 0 plus the acceleration of point P relative to 0. Now acceleration of 0 is fixed, as 0 is the fixed axis that we're taking. So this simplifies down to acceleration of P is just equal to acceleration of P relative to 0, which is broken down into the tangential as well as the normal components, giving us AP is equal to omega squared R plus alpha R, where omega squared R is in the tangential direction and the alpha R is in the normal direction. Point A is moving along the x direction at 2 meters per second. As a result, it's got constant velocity, so it has absolutely no acceleration. So we can say that acceleration at point A is equal to 0. Now from before, we know that acceleration at point B is equal to acceleration at point A, which is equal to 0, plus the acceleration of point B with respect to A. Now this can be split up into two components, the tangential and the normal component. So I'll skip a few steps and I'll just show that acceleration of B is equal to the normal component, omega squared r, plus the tangential component, alpha times r. Now we're very interested to find out what omega is because we haven't actually found it out yet, and we can do this through our velocity analysis. So we know that velocity at point A is equal to omega times the distance AB. To do this, I like drawing vector diagrams. You can do a number of different ways, but I'll show you how to do it through vector diagrams. So we can see that VA is moving towards the right at 2 meters a second. So let's call this VA equals 2 meters a second. We know that velocity of B is perpendicular and moving straight down. And we also know, if we draw it up, that the velocity of B with respect to A actually goes in this direction. So V of B with respect to A. We also know from our diagram above here that this angle is actually 30 degrees. Consequently, we can work out what the velocity of B relative to A is using the cos rule. So cos 30 is equal to 2 divided by velocity of B over A, and I'll just write it down for us. Omega is equal to velocity of B with respect to A divided by AB, where AB is given as 4 meters, which gives us 0.577 radians a second. Now, as the velocity of B relative to A is moving in this direction, we know that the angular velocity is moving in the correct direction as shown in the diagram. So with all of that in mind, we can write omega is equal to 0.577 radians a second in that direction, and we can continue solving our problem. Now, we know that the acceleration of B with respect to A in the normal direction is equal to omega squared r, which is equal to 0.577 squared times 4, which gives us 1.33, what is it? Yeah, 1.33 meters second squared. However, what we should also know is that the normal direction goes that way. So if we take the vector analysis, which goes from B to A, we can separate acceleration of A, acceleration of point B with respect to A into 1.33 cos 60I minus 1.33 sine 60J. And that's just really easy to construct that there is 60 degrees, that angle there. Now in the tangential direction, I'm going to run out of whiteboard space. I'll just write the whiteboard out and then do the tangential direction. Got the editing software. Now to find the tangential component. So we saw what the normal component was, and we know that the tangential component is perpendicular to the normal component, so it's going in that direction. So if we drew the vector up, we can see it's going in this direction. And this here will be 30 degrees. Now we know that the tangential direction is equal to alpha times the length of A and B, which is equal to 4. And if we separate it, this is equal to 4 alpha cos 30I minus 4 alpha sine 30j. Now we need to solve for alpha. So if we look at the diagram here, we can see that at point B, there's an acceleration going straight down, but there's no acceleration going in the I direction. So if we look at the first equation here, let's call that 1, and call this 2. If we take the I components only, we can say that 0 is equal to 1.33 cos 60I minus, sorry, that was a minus before at the front, so it's actually plus this, but it's a plus minus situation, 4 alpha cos 30I. From here we can solve alpha, and alpha is equal to 0.192 radians per second squared counterclockwise. From here we can solve what AB is, acceleration at point B is, which is equal to everything going in the J direction, which is going to be equal to negative 1.33 sine 60 minus 4 alpha, which is 0.192, sine 30, which gives us our final answer of 1.54 meters a second squared going down. That was the end of the question. Hopefully it was helpful for everyone. Ciao.